So this is a brief introduction to section 1.1, solving linear systems. So a linear equation is an equation like two x plus y plus z equals 5. If we're thinking of that as an equation in 3 space, it represents a plane in 3 space. So a linear equation, it has variables, their x, y, and z, and then their coefficients. And so that would be like this 2. There's actually a coefficient of 1 there, another one of 1 there. And then we have something on the right-hand side, which is really different. Maybe let's color it different. And that's the 5. So we might not have, we don't want to solve just, that's a plane, just one equation. We typically have a system, so that's more than one equation. So maybe we have another plane. Plus 7y plus 2z is equal to 9. So now I have 3 planes, and so I have a situation like the picture on our opening home page of our Canvas course, where we've got 3 different planes, and we're trying to find the particular, in this case, one point where they intersect. And so that's what a system is. We are trying to solve for x, y, and z that simultaneously satisfy all of these equations. And so if we were just doing this on our own, we would start trying to combine these equations to eliminate variables. For example, we might add the first and the third equation, and that would get rid of the x term. And then maybe we would do some other things to get rid of terms. But instead of that, what we do is we forget the x, y, and z, which are just placeholders, and form what's called the augmented matrix, which just has these coefficients. 1, minus 6, 7, 1, 1, 2. And then I sometimes might put a dotted line here just to indicate it's different. And so this is the right-hand side. So this is a matrix. It's actually called the augmented matrix of this system. And we're going to do operations on the rows, which would correspond to combining the equations. And so in particular, we're going to do what are called elementary row operations. And there are 3 kinds of them, and we'll talk about them in detail, but so they come in 3 flavors. And so instead of combining the equations, we would do these operations on the rows. So for example, one thing I might do is multiply the top row by minus 2, add it to the second row, and then replace the second row by that sum, which would amount to using these first 2 equations to eliminate x. So in any case, and we'll talk about how to do that, but we'll do several row operations, and then we'll get this matrix into what is called row echelon form. In this particular case, we'll see it looks like this. And so this is called row echelon form. So it's this triangular form, and so that means that it's going to correspond to a system that's easier to solve. So if we wrote out the system that corresponds to this bunch of equations, we'd have 2x plus y plus z equals 5, minus 8y minus z equals minus 12, and 2z equals 1. And so from that, we could solve this system more easily. So we could solve for z, and then plug in here and solve for y, and then plug y and z in here and solve for x. And so this process is called back substitution. Alternatively to this, instead of this, we could reduce this further. To avoid the back substitution, we could reduce this further, and it really just amounts to doing this substitution, in which case we would get 0, 0, 1, a half, 0, 1, 0, 11 eighths, and 1, 0, 0, 21 sixteenths. And this is called reduced row echelon form. And now it's completely trivial to solve. I mean, we can just read off what the solution is. Z equals a half, y equals 11 eighths, x equals 21 sixteenths. And that's what we would have gotten if we did the back substitution. So we'll talk about this in more detail. So I would say if we only had 2 planes, if we were only looking at, say, 2x plus y plus z equals 5, and 4x minus 6y plus z equals minus 2, so 2 planes, they would intersect in a line. And so now there's not going to just be one solution, there's going to be an infinite number of solutions. And so what we're going to want to do is to express this in a nice parametric form. Okay, in this case, there'll be one variable that we'll call the free variable, and we'll solve in terms of the free variable. So there'll be an infinite number of solutions. Okay, so that is what we will be doing, and we'll talk about it more in class. Thank you.